Hello, fellow future enthusiasts. On Demystifying, we do deep dives on science, futurism, and speculative technology. My name is Thor, and I will be your host today. In this video, we'll be introducing a new concept for a long-term exploration robot using a novel design. The first part of the video will discuss considerations of exploring the subsurface environments on other planets, and at the end I'll show some of the design process for the JACKI robot. Structures remaining from volcanic or cryovolcanic activity are invaluable destinations for research of all kinds. Lava tubes cut through many layers of material, exposing an area's geological history by the nature of their formation. If there are geologic or chemical signatures of ancient life-supporting biospheres on Mars or beyond, lava tubes are the ideal location to search for the evidence. These environments are protected from solar radiation and are more thermally stable than the surface. Unlike the surface, conditions inside these caves can remain the same for thousands of years. Tubes could trap volatiles such as water originating from the planet's atmosphere, so analyzing ice reservoirs could allow us to ascertain the history of the planet's climate in much the same way sea ice allows us to analyze ancient Earth's climate. Lava tubes are one of the few locations which might provide valuable science related to geology, climate, and biological activity. Lava tubes have another valuable use to human exploration. While we sometimes imagine these tubes housing large cities in science fiction, the reality is that these structures could be used as shelters by the very first explorers to safely avoid radiation while conducting initial surface studies. This paradigm implies building a temporary underground shelter instead of operating from modules parked on the planet's surface will be a top priority. Our discussion today revolves around novel robotics technologies, but we will focus primarily on the hardware and operational considerations of these systems. The specifics relating to pathfinding and evaluation of data into reliable survey data is mostly a software problem which can be discussed if that topic is of interest. For the sake of brevity, we'll start our discussion about the types of geological formations we know exploration robots face in the context of lava tube exploration on Earth. The longest uninterrupted surveyed lava tube on Earth is the Kazumura Cave in Hawaii, over 65 kilometers long. Other lava ducts are known to span well over 150 kilometers, but they are not surveyed. While there are clear commonalities between lava tubes of all kinds, the scale and composition of these structures varies depending on the body and the local geological history. We have observed Venusian lava tubes up to 1,000 kilometers in length, while the Moon and Mars have formations some 500 kilometers in length. These extraterrestrial tubes dwarf similar structures on Earth. However, we can look at tubes on Earth to inform a realistic discussion. Lower gravity on these bodies will result in some new types of obstacles we may not have on Earth, and we will attempt to anticipate these barriers. In terrestrial lava tube systems, we can assess 4 general types of obstacles to understand potential challenges. Transitional. Obstacles present at the opening of the tube including boulders, shear drops, and banks of fine regolith. In geology, this transitional area is either described as a skylight entrance or a rille entrance, depending on how the entrance was formed. Shear drops of hundreds of meters are a possibility in this area. Floor debris, rafted rock chunks transported by liquid flow or fallen from skylights. In geology, this debris is known as breakdown debris. Restrictions, narrowing of the tube either due to structure or debris to only a few meters or less. Collapses, areas of the tube open to the surface due to a collapse of the surface material which blocks access. Collapses might block entrances to the tube network as well, requiring excavation to gain initial access. It's worth noting these tunnels are often massive, ranging from dozens to perhaps hundreds of meters across. Some common structures inside lava tubes on Earth, such as stalactite curtains and ceiling overhangs, can easily block access to areas or hide them completely. The nature of lava tube formation will often produce parallel conduits produced from flows of lava at different times in the same region. These tubes will often intersect and collapse into one another, usually separated by relatively thin layers of laminate rock. Visibility becomes a real issue when exploring structures this large, not only in terms of light levels, but also given the possibility for key terrain features to be hidden from sight by rocks or ridges. Equipment needs to be elevated to provide sufficient line of sight for surveying, and the survey robot should be able to move freely in order to reduce the likelihood of missing key features. Deploying a fleet of independent vehicles to complete various geologic and resource surveys has been the commonly discussed approach to exploration of lava tubes in academia. Now that we understand some of the challenges faced by lava tube exploration robots, we'll look at real-life proposals towards the goal of exploring the lunar underground in order to inform our discussion. Notably the Lava-T, lava tube access via aerial tether. From these real-world studies, we can extrapolate to environments with similar challenges, including Mars and Ceres. Lava-T proposes a method to safely descend the sheer drop into the tube by unspooling a tether across the entrance, from which a second line attached to the vehicle is lowered. This operation could rely on a sky crane, but the Lava-T method is a more permanent solution for entering the cave network, so should be established via cables. The power needs of these vehicles mean they are typically tethered, wheeled drones. While there are obvious disadvantages to wheeled vehicles, the reality is the more optimal legged walkers we could send to other planets are just not reliable enough yet. We have never employed spider-like drones in the exploration of other worlds, and to apply this design will take dedicated missions or decades of testing. An appealing alternative is represented in the SphereX concept. This concept focuses on efficient data collection by using proven sensor technology and a system of line-of-sight data transmission to eliminate the need for cables and external power. The concept uses reaction wheels and a hypergolic thruster to maneuver a small LiDAR-equipped drone through the underground pits. One clear advantage here is that these drones can employ proven CubeSat components, reducing cost and development time. They cooperate in groups using line-of-sight communication, and transmit survey data back to their mother craft, executing more far-reaching missions as the mission progresses. The SphereX proposal highlights a problem. Low-gravity environments mean the force of friction is low, reducing the efficiency of rolling or wheeled locomotion. We will attempt to tackle this problem by reducing the amount of friction needed to achieve controlled locomotion. Must we depend on small wheeled survey drones to explore extensive lava tube networks? This approach will yield slow results without a large number of vehicles, and might be severely hampered by difficult terrain. Losing these vehicles is not really an option, since they will carry irreplaceable surveying equipment. Loss of equipment on the Moon is not really a problem, but replacing parts on Mars and other bodies is a huge debacle. Thus, a fleet of wheeled drones implies humans will be active in EVA and will be nearby enough to allow rescue of stranded or trapped drones when needed. This paradigm has numerous problems, which I hope this video will highlight as we investigate an alternative mission paradigm for exploring lava tubes. It's sensible to look for clues on how these survey operations might play out by examining similar human activities on Earth. Few relevant bodies have dense atmospheres, so quadcopter-style drones commonly used in cave mapping are not an option. Legged robots, such as those produced by robotics innovators such as Boston Dynamics, have a major flaw when applied to space exploration. They are less viable in low gravity due to the mechanisms used. Any moment of bad situational awareness could send these robots bouncing off terrain in a difficult-to-control manner in low gravity. This is because the legs function by applying impulses on the ground. If these impulses exceed what they should be, then the robot quickly goes flying. The legs must be telescopic or articulated, which also increases complexity, and even the simplest designs require very precise servos, which are heavier and more vulnerable to fouling. The only way to make legged robots highly reliable is to give them numerous short legs, which decreases their speed substantially, a condition not conducive in the context of exploring thousands of kilometers of tunnel. Another option is for snake-like robots using tracked articulated sections. These could move fairly rapidly across uneven terrain even in low gravity. While robots such as these are commonly seen performing disaster relief on Earth, they are of questionable usefulness in the context of surveying other planets. Even if locomotion could be perfected with these systems, the fact the robotic snake travels along the ground means it has poor visibility and could potentially miss geological features or fall into crevasses. This issue of poor visibility due to proximity with the ground is also present in more attractive designs. Louis Matteo's particle robots stand out as one example of a particularly effective solution to the problem of lava tube exploration. This design is nearly perfect for exploring wet and dry lava tubes in terms of locomotion, but has downsides inherent to relying on mechanical actuators. While this is acceptable on Earth, regolith on other planets and moons is much finer and more abrasive than Terran soil, and will degrade mechanical systems quickly when the vehicle relies on rolling through deep regolith. Another problematic aspect common to tracked, wheeled, or spherical robots is that they sit low to the ground, so their view of the terrain ahead is limited. This reduces their value as survey tools, although they can still perform basic exploration. I was not satisfied with the discussed solutions to this problem of lava tube exploration. If we plan to explore lava tubes on Mars, the Moon, and Ceres, we will need foolproof architecture to accomplish the maximum potential from the start of our exploration efforts. The science of space exploration has a need for subterranean survey architecture which functions in our modern spaceflight paradigm. It must be viable on repeatable, smaller payload vehicles, should not rely on extensive support infrastructure, and should be able to operate indefinitely without regular human interaction. Enter the JACKI system, the Jointless Autonomous Center of Mass Kinematic Interface. The JACKI system is comprised of two interactors, the autonomous robot itself and the locomotion truss. The JACKI system has an unusual method of locomotion. The truss acts as a track for the robot to move down its spokes, using a set of slotted motorized wheels and grabbing arms. The truss is made from hollow, lightweight aluminum, while the robot carries all survey equipment, cameras, and motors. The robot's motion as it traverses the truss causes a shift in the center of mass within the system, initiating a roll. As the roll proceeds, the robot continually alternates its direction diagonally, causing a precessional forward motion. The motion of the system produces sideways deviation with each step, resulting in a predictable snaking path. The clockwise or counterclockwise direction of rotation taken by the robot around each spoke allows the JACKI to select its movement direction, allowing the robot to perform both gradual and sharp turns as well as reversals while still moving. This design has major advantages over some similar concepts which could use the mechanism of a shifting center of mass to achieve locomotion. The limited number of spokes protruding from the truss means the vehicle always has a specific number of contact points with the terrain. The truss has better obstacle avoidance and traversal capabilities over a sphere as well, due to its ability to move through harsh terrain while making relatively little contact with it. Compared to wheels, a set of spider legs, or a rolling sphere, the JACKI system is cheaper and it has less complex mechanical components, while having a sample collection capability in addition to the ability to rapidly survey. The locomotion trusses come in many sizes for exploring different types of tubes. Some trusses occupy a spherical or diamond shape, and others are shaped like a flattened ball for more treacherous terrain. Some have branching fingers at the ends of their spokes for navigating across wide gaps. All of these shapes are made from the same hollow aluminum tubing. One interesting aspect of the two-part JACKI system is that the autonomous robot has an ability to reattach itself to other trusses. The JACKI must simply roll into contact with another unoccupied truss, and the autonomous robot can take hold of a new spoke, leaving the old truss behind. The robot carries a small axial flywheel system, which allows it to boost over obstacles. A larger flywheel could be used in higher gravity environments to increase climbing capability. The JACKI system offers some major advantages in the mission planning stage. The trusses can be built easily in situ or can arrive already assembled. They are made only from aluminum, so they can be manufactured on site with minimal effort. Deploying this architecture should be as simple as possible, both to minimize human involvement and reduce failure risk. The JACKI has no problems navigating surface terrain, nor traversing the boundary from surface to subsurface. Deploying a fleet of autonomous JACKI survey robots can theoretically be accomplished without human interaction. A sky crane could simply drop the robots and several additional empty trusses into a known lava tube entrance. This would require a tethered power source at the site, presumably laid before by an EVA team or originating with a mother craft landed nearby. The robots would then return to this location to swap out trusses, in order to deal with various terrain obstacles inside the tube or with other tasks. More than one autonomous robot can use the same truss simultaneously, so the possibilities are broad. We could keep a set of robots in reserve just for performing drone rescues or reacting to newly found tube systems. In comparison, driving a tethered wheeled robot down a steep pit carries the risk of the robot becoming trapped, especially if it is unable to see past nearby overhangs, as we've discussed. This comparison serves to show how a unique mission architecture benefits the JACKI system. These robots can perform numerous difficult tasks with zero operator intervention. They can delegate tasks among each other to quickly react to newly discovered obstacles or events using a neural network. They can rescue each other from impassable terrain. They can create temporary structures, such as bridges or ladders, to facilitate exploration by leaving their trusses spanning gaps. Even if the trusses are not directly touching, the autonomous robot is equipped so that it can transport itself short distances between spokes. We've argued that the JACKI system will be more resistant to becoming trapped, not only due to its mechanisms but also because the robots can cooperate to perform recoveries when these events inevitably arise. This capability comes from JACKI's independence from the locomotion truss. If unable to maneuver, the robot can detach and migrate to another nearby truss. Recoveries may involve the use of tool trusses. These features are single spokes with a tool end, typically hooks, shovels, or telescoping screws. Various scientific instruments can be deployed on these tools as well, but in the context of recovery, these are used to extend the reach of the robots. While other designs might require human intervention or complex dedicated recovery robots, the JACKI architecture attempts to solve all these problems at once. Consider the following hypothetical. A robot is trapped on the lip of a boundary shelf separating a main lava tube from a secondary duct and is unable to reverse due to rock debris. When two robots arrive at the scene to start recovery, instead of attempting to traverse the gap and risk becoming stuck as well, they place one of their locomotion trusses across the gap and both return to their task on a single truss. We can afford to use the truss sections in a disposable capacity like this due to their simplicity and extremely low cost. We've already alluded to some of the shortcomings of the JACKI architecture. The primary weakness lies in the system's inability to produce sufficient force to traverse taller vertical obstacles. We have two compounding solutions to this issue. Firstly, having access to larger trusses allows robots to swap to one with spokes longer than the height of the obstacle, allowing it to gain purchase on ledges and slopes. Secondly, a set of small flywheels capable of producing a torque force greater than the force of local gravity can be utilized to accomplish climbing and even powered hops. The ability to perform powered jumps implies a heavier robot with more power draw, so this ability should never be used as a primary means of locomotion. The travel distance of the wheels which propel the autonomous robot across the truss is greater than the distance the vehicle will travel, so these systems are relatively energy efficient due to low resistance on servos. To move, the unit needs to lift less mass than the combined mass of both the robot and the truss. Another potential failure point is represented in the lightweight spokes of the truss assembly. These are hollow aluminum and could become bent by impact. Consider the outcome of damage to alternative locomotion systems in comparison. A broken wheel or a spider leg would almost certainly result in a total loss of mobility. The JACKI system does not need every spoke on its truss to function. Even multiple adjacent damaged trusses can be compensated for by changing the path of the autonomous robot to use other spokes. While mobility is lessened following damage, the drone can still function well enough to find an undamaged truss and transfer to it if incapable of carrying out its mission. While ideal for lava tube systems, which by nature tend to not be very steep, the climbing performance of these robots makes them ill-suited for certain types of cave networks. It makes sense to eventually diversify the exploration architecture and use to improve capability once lunar manufacturing becomes possible. Lava tubes offer a unique opportunity to experiment and practice our cave exploration technologies on Earth before we reach other bodies, such as Luna, Mars, Ceres, and even Io and Venus. The more we develop our autonomous cave exploration technologies on Earth, the more prepared we will be to study these vital scientific and habitation assets. So the first major challenge I ran into trying to simulate the JACKI robot kinematically was how do I accurately model a simulation with enough flexibility in it to change all the factors that I need, and do all of this inside the software that I have access to, being Blender. Blender has limited features to accommodate complex physics simulations. It can do a great deal with code, but coding would require me to ascertain the physics properties of the various objects, which is pretty time-consuming. Plus, I knew I could get it working without code, somehow. Blender can't do multi-mass objects very well. An object that's broken up into distinct areas with varying mass in each, it doesn't really understand how to link objects together in that way, so I had to figure out some shortcuts. In the end, it wasn't that hard, just required a little bit of clever parenting. It turns out, from my experiments, I found that Blender can accomplish some pretty decent and realistic physics, but it requires a lot of physics iterations to reach this level of realism that I'm looking for. I'll probably look at using Project Chrono in the future to reduce simulation time for projects like these. I settled on a coordinate mass system with each spoke representing a discrete mass on its end. This isn't 100% accurate to the real physical composition of one of these systems, but it's close enough. It does allow me to get a one-to-one kinematic representation of how this object would act. I could change the mass of each point in the truss to represent the change in the center of gravity. Changing the mass slightly to model the robot's movement around each spoke can also be done, and I do this by adding smaller weights to the lateral weighted ends of the truss. This was important because the potential instability that occurs when the truss is revolving should be modeled. It's pretty important to understand how that works, especially when the JACKI is moving up or down hills or around obstacles. The weight distribution of the spokes is slightly irregular, obviously. The tips of the spokes are lighter to reduce the amount of force needed to overcome static equilibrium. So what this means is that the very tip of the truss itself actually doesn't have any mass. The mass is concentrated a little bit further in towards the center of the entire truss assembly. The reason for this is that the ends of the trusses in real life would actually be hollow and made of a thinner material than the rest of the truss. By concentrating mass at the very center of the truss, rolling is easier to achieve because there's less mass to have to move at the very edge of the rotating system.